In this lecture, we're going to look at Chinese mathematics, taking it up roughly to about 1300 AD. In my very first lecture, I talked about different sources of mathematical ideas, one of which is civil administration, another is navigation and surveying, and the third is astronomy. And as I said, all of these come into play in all of the great mathematical cultures, but different ones come to the fore in different cultures. So, for example, for the Babylonians and the Egyptians, as we saw, the dominant mathematical theme was what was needed for civil administration. When we get to the Greeks, the dominant theme is navigation and surveying, and this would influence the Greek decision to put their emphasis on proportion and on geometry. As we saw in the last lecture with Indian mathematics, really the dominant source of mathematical work came from astronomy. It was really the astronomers who were making the progress in mathematics. As we now shift to China, we're going to see that we go back to a mathematics that primarily comes out of civil administration, very similar to the sources for the mathematics in Babylon and also in Egypt, although also here navigation, surveying, and astronomy will be very important sources for the mathematics that is created. Our recorded record of mathematics in China begins with the early part of the Han Dynasty, what is known as the Western Han Dynasty or former Han Dynasty, going from 206 BC to 25 AD. And what made this particular time particularly propitious for the development of mathematics connected with civil administration is that this is the first Confucian dynasty in Chinese history. So this is a dynasty that is really built around the idea of Confucian scholars, people who are drawn out of the general population and trained in the kind of mathematics and philosophy and jurisprudence that they would need in order to be civil administrators. And so an important role in the Western Han Dynasty was that of the teacher, that of the person who would train the future Confucian scholars. And these people needed textbooks. And the Chinese textbooks in many respects are similar to the kinds of textbooks that we saw in Babylon and in Egypt. These are problem books. These are books that set out lots of problems that a future scholar would need to be able to solve in various contexts, and then would work out the solutions. We have two manuscripts from this time. The first of these is the Chupei Suanjing, roughly translated as the mathematical classic of the Chu Nomen. And this was written possibly in the 1st century BC. It might go back even earlier than that. And this deals with problems of similar triangles, very much involved with questions of surveying. You find the Pythagorean theorem stated quite clearly in this particular work. There also are methods for calculating square roots. Another book that comes out of this same period is the Chucheng Suanshu, or Computational Prescriptions, in 9 chapters. And this does a lot of work with finding areas and volumes. Again, we find the Pythagorean theorem. We also find linear equations. So these now are systems of equations, situations in which you've got several things that are unknown, but you've got several relationships connecting them. Problems like this can be found in the ancient Babylonian mathematics, but we also see it reappearing here in the very earliest known Chinese mathematics. There are also general rules for calculating square roots and cube roots, and the kinds of problems that are dealt with in this particular book involve problems of surveying, problems of commerce, problems of tax collection. And they used the same system for representing numbers that was used in India. The largest number that is actually represented in this particular book is 1,644,866,437,500. So they clearly were comfortable with working with extremely large numbers. Even more important than that, the Chinese at this time, this is still about the 3rd or 2nd century BC, were not only using fractions, but they also were using decimal fractions. So they extended this idea of a decimal representation, not just units place, tens, hundreds, thousands, but also moving in the other direction and looking at tenths, hundredths, thousandths. And in this book, we do have decimal fractions expressed out to thousands. Also here, again, we're talking 2nd, 3rd century BC. The Chinese are using negative numbers. Now, as I said, it would be Brahmagupta who was the first person to really accept negative numbers as legitimate solutions to mathematical problems. The Chinese were not there yet, but they were the first people to use negative numbers as intermediate steps in some sort of a calculation that might need to be done. Buddhism is introduced generally into China around the 1st century AD. And sometime shortly after that, we begin to get the Indian astronomical texts being brought up, texts written in Sanskrit and introduced into China. And there are references to Chinese monks who would make a pilgrimage to India and be asked to come back with the mathematical texts. And so there was some transfer of mathematical knowledge from India into China in this time. We know that the Chinese built their ideas of trigonometry and began to work with trigonometric functions based on what they had learned from the Indians. Although this is one of the few places where we actually are aware of how mathematics traveled from China to other places or from other places to China. There is very little other direct evidence of influence between China and the other civilizations that surrounded it. It would take a while for the Chinese to begin to use 0 as a placeholder. They did not start using it until many hundreds of years after the Indians had begun to use it. But around the year 1000 AD, the Chinese were using 0 as a placeholder, although well after that, many of the Chinese mathematicians would continue to use special symbols for 10, 100, 1,000, or tenths, hundredths, or thousandths. The first actual Chinese mathematician that we know by name was Lui Hui. He lived sometime late in the 3rd century AD, and he is best known for his work, the Haidao Suanjing, or the Sea Island Computational Canon. And this was really a work that was looking at questions of surveying. And the name of this particular work, Sea Island Computational Canon, comes from the very first problem that's explained in the book, and that is trying to determine the height of a mountain on an island. So you are not on that island, you're somewhere offshore, but you see that island and you want to determine the height of the mountain. And you cannot actually determine your distance from where you are to the base of the mountain. What you have to do is take several different observations from where you are on this opposite shore. And what Lui Hui does is to explain how to use the idea of similar triangles in order to work out what the height of this mountain is going to be. We also very significantly find in this particular work the very first Chinese proof of the Pythagorean theorem. Now, this is not the first known proof of the Pythagorean theorem. As I said, this was known earlier, probably sometime in Greece between the time of Pythagoras and the time of Euclid. But Lui Hui does work out an actual proof of the Pythagorean theorem. Very significantly, he also works out a general method for finding areas and volumes that is equivalent to the method that was developed by Eudoxus of Cnidus and then described by Euclid and used so effectively by Archimedes, this idea of method of exhaustion, and that is used by Louis Hui. Louis Hui also comes up with exactly the same idea for approximating pi that Archimedes had discovered. This idea of first finding the circumference of a regular hexagon that is inscribed inside a circle, and then doubling the number of sides. As I said, Archimedes stopped when he got to a regular polygon of 96 sides. Louis Hui took this a step further. He went all the way up to a regular polygon of 192 sides and used that to come up with the approximation which he actually states that pi is approximately 3.14. And so he gives it as the decimal using tenths and using hundredths. And Louis Hui also does something else. Even though decimal fractions had been used earlier, it's not quite clear how much mathematicians of that time were aware that you could continue decimal expansions as far as you wish. And Louis Hui specifically states that decimals can be expanded to as many places as you might wish. If you've got any distance, you can always try to find an approximation to its value by taking progressively smaller units, so taking tenths of tenths of tenths as far out as might be needed. Now, I said that Louis Hui came up with a very accurate approximation to pi 3.14. As most Chinese school children know, the most accurate approximation to pi from this time comes from a mathematician who lived late in the 5th century, Zhu Chongqi, and he came up with a rational approximation to pi of 355 over 113. It's a remarkable accomplishment. We don't know exactly how he achieved it, but he might have been using the same idea that Louis Hui did of taking polygons with progressively more sides. 355 over 113 is accurate to within an error of less than 3 parts in 10 million. And this would be the most accurate approximation to pi that would be found for well over 1,000 years. It's also an easy number to remember, especially if you think of fractions the way the Chinese thought of fractions and the way they still do, which is that you give the denominator first and then state the numerator. I've always thought this makes a lot of sense because the denominator tells you what kind of thing you're talking about in the fraction, and the numerator then tells you how many of these you've got. And so if you take this fraction, 355 over 113, and instead describe it as denominator 113, numerator 355, you've got 113,355, and that's a very easy sequence of numbers to remember. And as I said, it gives an extremely accurate approximation to pi. There's another problem that the Chinese worked with at this time, and it's a problem that I've alluded to in thinking about how you apply numbers to time. One of the problems as you try to apply numbers to time is that you've got different units to work with. You've got the day, you've got the lunar month, you've got the solar year, and how do you decide when all of these are going to line up? Now, obviously, astronomers all the way back to the Egyptians and the Babylonians must have worked with this. But the first time we actually see a method of solving this problem, knowing when different cycles are going to line up, comes to us from the Chinese mathematicians. And the first time that we see this is in a work called Sun Si Xuanqing, or Sun Si's Computational Canon. We don't know exactly when it was written, sometime between 280 AD and 473 AD. But what it does is to provide a method for finding out when different cycles are going to line up. It's something that today we call the Chinese remainder theorem. And the actual example that is given in the Sun Si Xuanqing is the following. We consider a cycle of length 3, and we are 2 units into that cycle. We consider another cycle of length 5, and we know that we are 3 units into that cycle. And we consider a third cycle of length 7, and we know that we are 2 units into that cycle. Now, another way of thinking about this, and the problem is, how long ago were all of these cycles lined up? And the situation is exactly equivalent to, we want to find a number so that when we divide it by 3, we've got 2 left over. How long has it been going through cycles of 3 until we get 2 into a cycle of 3? Take this number, divide it by 5, and we want a remainder of 3. So again, how many times do you go through a cycle of 5 and then go 3 more into it? And we want a number which also divided by 7 leaves you with a remainder of 2. The answer to this is 23, that you have to back up 23 time units to get all of these lined up. 23 divided by 3 leaves 2. 23 divided by 5 leaves 3. 23 divided by 7 leaves 2. Now, in this work, the method for finding these solutions is not explained, but it does give an indication that this was being studied, and a little bit later I'll talk about one of the Chinese mathematicians who actually did find a method for proving it. The next significant mathematician to come along comes at the very beginning of the Tang Dynasty. The Tang Dynasty began in 618, it ended in 907. And one of the very important people at the beginning of the Tang Dynasty was Lei Chunfeng. He was the director of the Astronomical Observation Service, and of course, as the chief astronomer of the Tang Dynasty, he would also be the chief astrologer of the Tang Dynasty. And if you're setting up a new dynasty and you're deciding where to locate your capital and how to build your main buildings, you need to know what the astrological prognostications are. What is a good time at which to launch a particular endeavor? And so Lei Chunfeng became very important for his astronomical work. But even more important than that, he looked back at all of the mathematics that had been done in China up until that point. And he was given the task of trying to pull it all together. What had happened over the centuries is that many of these mathematical texts had been corrupted. They had been copied and recopied and recopied, and mistakes had crept in. And there were places where different versions contradicted each other. There were different methods in different books that contradicted each other. And so Lei Chunfeng took on the responsibility of taking all of the mathematics that was known in China at that time and pulling it together in what would come to be known as the 10 computational canons. This is a work that was done over the period 644 to 648 AD, and while it's called the 10 computational canons, in fact, they did pull on more than just 10 mathematical works. There were probably at least 12 or 13 different mathematical works that were combined into this. And not only did they take these works and correct the corruptions that had come into them, but they also provided extensive commentaries. And so, much in the same way that Euclid in 300 BC took all of Greek mathematics and re-established it, clarified it, and made a foundation on which further mathematicians could build, Lei Chunfeng did exactly the same thing for Chinese mathematics in the middle of the 7th century. From here, Chinese mathematicians would begin to work on problems of general polynomials. And it's not quite clear when they began to work with polynomials and exactly how the work that they did with polynomials related to the work that was being done on polynomials in India. In the next lecture, I'll also be looking at Islamic work in mathematics, and we're going to see polynomials coming in and playing a very important role there. And so we've got 3 great centers toward the end of the first millennium AD that are all working, getting to this idea of a polynomial of general degree. We would love to know how they interacted, if there was any kind of exchange, the fact that all three centers of civilization were working on similar kinds of problems at exactly the same time suggests that probably there was some kind of communication, although it probably was quite imperfect. One of the important Chinese mathematicians from slightly after the year 1000 was Jia Xian. Jia Xian was a court eunuch. He lived sometime in the middle of the 11th century. And Jia Xian is credited generally with being the first person to come across Pascal's triangle. Now, Pascal's triangle is a triangular arrangement of integers that has ones down the outside edge, and then the numbers inside are obtained by adding the numbers that are diagonally above it. So I've got 1 and then 2 ones, and the next row is 1, 2, 1, and the next row is 1, 3, 3, 1, and the next row is 1, 4, 6, 4, 1. This is named for Blaise Pascal because of the work that he did on this particular triangular arrangement of numbers in the 17th century. But in fact, even Blaise Pascal realized that it was much older than himself. His name was associated with it because of all the work that he would do on it. And the place that this comes from is the problem of expanding binomials. So I'm looking at a binomial, 1 plus x, so it's a two-term algebraic expression, and I want to begin to multiply it by itself. 1 plus x times itself is 1 plus 2x plus x squared. If I multiply that by 1 plus x, I get 1 plus 3x squared plus x cubed. And if I multiply that by itself, I get 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. And if you look at those coefficients, those are exactly the numbers in Pascal's triangle. And so what Pascal's triangle does is it gives you an easy way of remembering or finding the coefficients as you take 1 plus x and take progressive powers of it. And the purpose of doing this, the reason that Jia Xian studied this particular triangular arrangement, the reason that he was looking at these binomial expansions, ways of getting the expanded polynomial out of 1 plus x raised to a power, is that this is a very powerful way of approximating the root of a polynomial, the place where a polynomial actually is equal to 0. And so we know that by the 11th century in China, these Chinese astronomers and mathematicians were interested in working with general polynomials and trying to find out those values at which the polynomial would equal 0. Now, for some polynomials, this happens at an exact integer or maybe a nice fraction. Most of the time, the location of this 0 is going to be some irrational number, some number that cannot be represented as a ratio of integers. And so the best you can do is to get a good decimal approximation to the number in question. And you can use Pascal's triangle, you can use these binomial expansions in order to get these roots to whatever accuracy you actually need. Now, this would be then developed by Li Qi. Li Qi, who lived 1192 to 1279, wrote a work that is known as the Zeyuan Haijing, which means mirror like the ocean, reflecting the heaven of calculations of circles. It's a bit of a flowery title. It's a book that was written in 1248, and it has a lot of mathematics in it. We find many geometric techniques, but he also specifically addresses this idea, the problem of finding roots of polynomials to arbitrarily high degree. And it's Li Qi who references Jia Xian and says that he got this idea, and in fact, by the time that Li Qi is writing, this method of using Pascal's triangle is called the old method. It was at least a couple of hundred years old at this time. But Li Qi, whose manuscript we do actually have copies of today, lays out in a great deal of detail how to find the roots of an arbitrary polynomial by using Pascal's triangle. Another one of the Chinese mathematicians who was also working at this time is Qinju Shao. He lived roughly 1202 to 1261. And one of the things that he did was to take the Chinese remainder theorem. So this is the problem of astronomical cycles, and you want to know when was the last time they all lined up. And if you know the last time they all lined up, that will enable you to determine the next time they will line up, and the time after that when they all line up. And so Qinju Shao, even though the Chinese remainder theorem had probably been solved earlier, he becomes the first person to actually explain how it works and show how to use it in any situation with any number of cycles of any length. And one of the examples that he gives is a number that is 32 units into a cycle of length 83. It is also 70 units into a cycle of 110, and it is 30 units into a cycle of 135. In other words, what we want is the smallest positive number, so that if we divide it by 83, the remainder is 32. If we divide it by 110, the remainder is 70. And if we divide it by 135, the remainder is 30. And I'll leave that out there as a problem for you to work on. I'll give you a hint. The number lies somewhere between 20,000 and 30,000. Chinese mathematics of this era would really come to its culmination in the late 13th century, under a time when Kublai Khan was the ruler of China. And one of the great works that was written at this time is the Siyuan Yujian, the trustworthy mirror of the four unknowns. Zhu Shijia was the author of this. It actually was written slightly after the time of Kublai Khan. It appeared in 1303, but it was built on a lot of work that had been done in China at the very end of the 13th century. And this is an incredible work for the sophistication with which Zhu Shijia was able to work with polynomials. I had mentioned when I talked about the Indian use of interpolating polynomials that a general formula for interpolating polynomials using not just first differences, second differences, but third differences, fourth differences, as far out as you might want to go. That's something that Isaac Newton discovered, and it's known as the Newton interpolation formula. But what we find here is the Newton interpolation formula in its full generality that clearly was known to the Chinese mathematicians at the end of the 13th century. Something else that Zhu Shijia was able to do at this time is to work with Pascal's triangle, this triangular arrangement of numbers, and find ways for combining these binomial coefficients. And so a result that would come later to be known as Vandermon's formula, and Vandermon was a European mathematician of the 18th century. Vandermon's formula was first discovered by Zhu Shijia. This is a formula for taking the sum of the binomial coefficients that come up on a particular diagonal, and then finding what they equal in terms of a binomial coefficient. The evidence is that Chinese mathematics begins to disappear after the 13th century, and that may well be due to the chaos created in China after the fall of Kublai Khan. China broke up into a lot of small warring states, and mathematics really stops being developed in China for quite a few hundred years. In the next lecture, we're going to switch to Islamic mathematics and the emergence of algebra. And one of the great questions that I would like you to keep in mind as we come into this next lecture is how much of the Islamic mathematics actually was drawing on what had been happening in China. We know that Islamic mathematics built heavily on what had been happening in India, but we're not sure how much Chinese mathematics influenced what would happen in the Islamic world.